Momentum is one of the most fundamental concepts in physics, and for engineers it is a guiding principle in understanding how forces act during motion and impact. Defined as the product of mass and velocity, momentum captures both the weight and the speed of an object, making it a critical factor in predicting how systems behave under dynamic conditions. For civil and mechanical engineers, momentum is not just a formula, it is a measure of safety, stability, and performance. The principle of conservation of momentum states that in the absence of external forces, the total momentum of a system remains constant. This idea lies at the heart of analyzing collisions, whether between subatomic particles or large vehicles on highways. In engineering, this principle allows us to predict outcomes in impact scenarios and design systems that minimize damage while preserving stability. Collisions highlight the practical significance of momentum. In elastic collisions, kinetic energy is preserved, whereas in inelastic collisions, part of the energy is transformed into heat, sound, or deformation. Cars, for example, are designed with crumple zones that absorb momentum transfer during a crash. By extending the time of collision, these zones reduce the force experienced by passengers, turning a destructive event into a survivable one. This is momentum in action, applied physics saving lives. In civil engineering, momentum appears in less obvious but equally critical ways. Consider the driving of piles into the ground for the foundation of bridges and tall buildings. Heavy hammers deliver momentum to piles through repeated impacts, ensuring deep and secure anchorage. Similarly, when analyzing pedestrian bridges or large stadium structures, engineers must account for dynamic loads created by moving crowds, where momentum transfer affects stability and comfort. Impulse, defined as force multiplied by the time over which it acts, is another key concept engineers use to manage momentum. Increasing the collision time reduces peak forces, a principle applied in airbags, helmets, and even earthquake-resistant structures where energy must be dissipated without catastrophic collapse. In each case, managing momentum is at the core of ensuring structural safety and resilience. Momentum also plays a role in large-scale events, from vehicles colliding on roads to trains, ships, and even aircraft. Each case demands careful engineering analysis of momentum transfer, not just to predict motion but to design safer transport systems and stronger infrastructures. Understanding momentum equips engineers to anticipate risks, design protective features, and build structures that withstand both expected and unexpected forces. Ultimately, momentum reminds us that motion carries consequences. Whether in the crash of a vehicle, the strike of a hammer, or the sway of a bridge, engineers must constantly calculate and control how momentum is transferred. By mastering this principle, we can build safer roads, stronger structures, and more resilient technologies. This video is part of the series, Physics for Engineers: Foundations that Build the Future, an initiative of the Physical Sciences Consultorium. If you found this exploration insightful, make sure to subscribe, explore more content from PSC, and join us as we continue connecting the elegance of physics with the impact of engineering.